Dear colleagues, ladies and gentlemen, it's my special pleasure to welcome Riccardo Urso from the INAF-Osservatorio Astrofisico di Catania, who will be talking about the effects of low energy cosmic rays and solar particles on pristine and organic matter. Since I'm in astrochemistry and astrobiology, I've always been very impressed by the research, which is just in this special area done by the Osservatorio Astrofisico di Catania, and we had also a very nice meeting on this subject in Catania some time ago. Now, I don't really want to talk longer and give over the word to Riccardo, who is also leading one of our subgroups in the European Astrobiology Institute. Well, Riccardo, the floor is yours. Thanks for coming, for agreeing to talk.
Thank you, Wolf, for the introduction and for the invitation. Yes, so in this seminar, I would like to share with you some of the research that is going on in Catania and also in other institutes we work with on what concerns the effect of energetic particles. I have some background. Okay, that should be fine now. The studies that we do on the effect of how energetic particles can interact with solid phase matter and trigger deformation of organics, but also their destruction. But first of all, let's start with what is organic matter. It's interesting to how looking back in the past till the 18th century, organic matter was strongly associated with life. Vitalism was basically the thinking that all organics possessed a vital force, so they couldn't be produced in our laboratory. I think that was then disproven when systematic studies on organic compounds performed in the 1800s showed how we could produce organics. And in 1828, we have what is seen as the moment when organic chemistry started with the production of urea, a substance that was known to be present in urine, was first reported. So organic is at the basis of life, which in turn is based on some of the molecules that we see in the slides. We have amino acids, sugars, and nucleobases. Without these molecules, life as we know it could simply not exist. And all these molecules are based on carbon, on the carbon chemistry, with the presence of hydrogen and other heteroatoms such as oxygen, nitrogen. We also have sulfur and so on. If vitalism would still be a thing, we would definitely be sure of the existence of life elsewhere in the universe, because organics are a relevant fraction of matter in extraterrestrial samples such as meteorites. Here we have three examples of different meteorites. One of the most well characterized is the Murchison meteorites that you see here on the left. They do not come only in the shape of stones, big or less big. They also come in the sides below a few millimeters in the micrometer range, such as in the case of interplanetary dust particles, which are collected in the stratosphere by balloons, or micrometeorites, like in the case of ultracarbonaceous Antarctic micrometeorites that are collected in the ices in Antarctica. We have the chance of analyzing these samples in the laboratory, and so to use a variety of techniques which opened us the possibility of reveal the high chemical diversity of the organic matter in these extraterrestrial samples. Here there are some mass spectra acquired on the extracts of the Murchison meteorite. Each of these peaks is associated to an organic molecule. So you see thousands of different compounds. We also have infrared spectra, which normally show peculiar absorption bands at around 2,900 centimeters to the -1, which are attributed to the CH stretching modes typical of organic materials. And still, infrared and Raman spectrometry performed on these micrometeorites that showed the abundance of organic matter in these samples. There's a debate, let's say, on how pristine these organics could be. And that's due mainly to the alteration that these particles can suffer when entering the atmosphere, but also on the contamination that can happen on Earth when they are delivered, when they arrive on our planet. So constant efforts were always put in characterizing their parent bodies, so the bodies from which meteorites originates. And this is the case of asteroids and comets. Here we have two examples of these bodies that were thoroughly studied by space missions. In particular, the asteroid Bennu was studied by the OSIRIS-REx space mission, which allowed us to observe absorption features in the infrared spectra, which are due to the CH stretching bonds of organic matter present at its surface. And for what concerned the 67B comet, the Rosetta mission also revealed the presence of these absorption features. Of course, we're talking of two completely different bodies. They have completely different origins and evolution histories. But this gives in the direction, this suggests that organic matter is present in a variety of environments in the solar system. If you still don't believe that organics are there, well, here there are samples that we collected directly at the surface of two asteroids, Ryugu, where the Hayabusa 2 spacecraft collected samples and allowed us its analysis here on Earth, and also the samples acquired by OSIRIS-REx on Bennu. Here you see how these grains from both the asteroids are very dark and also very rich in organics. On Bennu, we have a variety of different chemical families, from amino acids to nitrogen heterocycles, which are structurally similar to nucleobases. Each peak that you see here in this mass spectra of Bennu samples, as well as each of the dots that you see in this graph, are all related to different organic molecules in these two asteroids. And almost 20 years ago, we also sampled directly from the coma of a comet some dust grains that were collected and trapped in this huge device, where each of these cubes are made of aerogel, which is a very light material that was meant to stop and preserve cometary dust particles that were then shipped to Earth and that we were able to analyze, and where we also observed the presence of organics. But still, if we move farther out in the solar system, it is extremely nice to reveal the presence of complex organic material also on the surface of Pluto, which is the object that you see on the left, where organics are characterized by this very red color, and where they are present together with ices. The same is true for Arrokoth, which is the farthest object we've ever visited in the Kuiper belt, which shows this nicely orange-reddish color, and as well as the presence of ices. In particular, we know about the presence of methanol ice. So trans-Neptunian objects located in the outer solar system have a peculiar characteristic. They are thought to have experienced just slightly alterations, and so we believe that the matter that they contain is really pristine matter that was only or possibly not at all altered during the 4.5 years of evolution of the solar system. What are we talking about? Well, it's not only Pluto and Arrokoth. The trans-Neptunian are a lot of bodies located beyond the orbit of Neptune. And here you see how many trans-Neptunians we knew together with comets and centaurs in 2001. This is what happened in 2016. This is the number of TNOs that we knew back then. And this is the most updated map that I found. I am sure that the discoveries went through, and so we now know way more objects. And recently, the James Webb gave the opportunity of observing many of these TNOs in a program led by Noémie Pinilla-Alonso, the DISCO project, and several bodies in the range of 100 to 900 kilometers were observed in the infrared, and they revealed a clear distinction in three main groups. This bowl-type group contains mainly water and carbon dioxide, ices, at the surface. But if you look at these other two families, they contain quite some carbon-bearing molecules and also hints of the presence of complex organic matter. What is interesting is that these authors used all these infrared absorption features and the presence of complex organic to trace back the history and the evolution of trans-Neptunian objects, and they were able to locate their formation location in the protoplanetary disk. So studying organic matter does not simply allow us to shed light on the chemical complexity that we can have in the solar system, but also on the history and the evolution of the solar system itself. Now, how and when do these complex organic molecules form? There are two main scenarios. The nature scenarios suggest that complex organics were formed already in the diffuse interstellar medium, or maybe later on in the molecular cloud or in the protoplanetary disk, and that bodies like trans-Neptunian objects accreted these organics when they formed. Another scenario is the nurture scenario, which sees this trans-Neptunian as formed by simple carbon-bearing ices, and where complex organics formed later on during their life in the solar system. In the nature scenario, so we need to understand what were the precursor of these complex organic materials that could form already during the star formation process or during the solar system formation process. And to do that, we can look at similar region where new stars and are forming right now, such as in the case of NER 38, which was the target of James Webb observations recently, and where you see that the bright spot are stars that are now forming, and they are surrounded by a cloud of gas and dust. This is the infrared spectrum that the James Webb Space Telescope allowed us to observe. What we observe is molecules in the gas, but also molecules in the solid phase. And in a moment, we will see what do I refer to. And as you can see, we see less than 10 chemical species. Some of them contain carbon, and so some of them could be the precursor for these complex organic materials. The chemical situation is even more complex if we take into account what has been detected in the gas phase. We have hundreds, up to 330 molecules detected so far. So what are the chemical processes that could lead to the formation of complex organic molecules in these regions? We have various chemical pathways that regard both the gas phase reaction that happen between the molecules that surround the stars during their formation, and we also have reaction that can take place in the solid phase. In this case, we have ices that are stuck on the surface of silicate grains because the temperature in this region is really low. We are temperature slightly above 10 Kelvin. So everything can freeze on the cold surface on these very small grains made of silicates of carbonaceous material, and ices, a layer of ices can form on their surfaces. These ices are mainly composed of the molecules that we observed with the James Webb. So we have water, we have CO, we have CO2. We might also have nitrogen-bearing molecules. What happens is that all these molecules, which are condensed and in contact with each other on the grains, are exposed to energetic charged particles and UV photons, which are able to release their energy to ices, triggering chemical reactions. In particular, what happens is that energetic charged particles break the molecules that they find along their path. These molecules break into radicals and molecular fragments that recombine, forming species that are different than the original molecules. So this is how we could trigger chemistry in the early stages of the star formation process. But energetic radiation also has a very important role in the solar system, and thus in the nurture scenario, where complex organic could have formed directly at the surface of TNOs and other pristine bodies, assuming that they were only composed by pristine ices available in the protoplanetary disk. In this case, in this cartoon, you see how the particles emitted by the sun do not kill us because we are protected by the magnetosphere of the Earth. On Mars, which lacks of a magnetosphere, there is an atmosphere that significantly limits the flux of particles on the surface. And on Jupiter as well, we have a very significant magnetosphere which protects the planet from the bombardment. But asteroids and trans-Neptunian objects lack of both atmosphere and magnetic fields. So particles can arrive on their surfaces and trigger chemical reactions that form organic matter. In particular, we have three families of particles in the solar system. We have cosmic rays, which are among the most energetic particles that likely are shielded by the heliosphere. And then we have the particles emitted by the sun, so solar, wind, and solar energetic particles. All these three families of particles have very different energies. Cosmic rays can penetrate up to tens of meters because they have really high energies. Solar energetic particles have a wide range of energy, and they can penetrate between a few microns and up to tens of centimeters, while solar wind have a very low energy, so they can penetrate only a few hundreds of nanometers of solid phase surfaces. This is very relevant for chemistry because solar wind ions are the most abundant. Their flux is way higher than the flux of solar energetic particles and cosmic rays, but they can only alter the very upper surface of TNOs, for example. So they can't really change the chemical composition deep in these bodies. Now, all we know about the effect of radiation and of energetic particles on solid phase matter comes from laboratory experiment. This is the setup that we have at the Laboratory for Experimental Astrophysics in Catania, and that we use to simulate the effect of cosmic rays and solar particles on solid phase material. On the left here, you see the ion accelerator that we use to produce an ion beam, which is focused in a simulation chamber where we can produce icy films by depositing volatile molecules that condense on a cold substrate. So what we do is to deposit an ice, expose it to energetic radiation, and then we perform the analysis by means of infrared spectroscopy of the chemical changes that took place during the irradiation. So let's see what happened to a simple ice, which we might observe in star-forming region. For example, an ice that is made of solid carbon monoxide, and whose spectrum correspond to the black line that you see here. This is what happened when we turn on the ion beam and we process the carbon monoxide ice. We produce a lot of different molecules. In this case, we observed the formation of carbon chain oxides, which are nice molecules because they are made of a skeleton of carbon atoms with 1 or 2 oxygen at the termination. So you can imagine it's nice to visualize how this process can basically trigger the formation of long elongated chains starting from a very simple molecules that is ubiquitous in star-forming regions. The chemistry is even more complex if we take into account mixtures. In this case, we have water, methane, and nitrogen ices exposed to different ion beams, where we observed the formation of formamide, which is a very relevant molecule in astrochemistry and astrobiology, as several works showed how it is a precursor of prebiotic compounds. An interesting aspect that we observe here is that the chemistry not only depends on the pristine composition of the ice, but also on the type of radiation that we take into account and on the dose, which is the amount of energy that the sample absorbs with interacting with the ion beam. For example, here we notice a different production of HNCO, isocyanic acid, whether we use helium ions up to a dose of 300 electron volts per molecules, or whether we use protons up to 240 electron volts per molecule. Changing the ice, in this case, we are using water, methanol, and ammonia ice, and we expose it to radiation. We can also study the chemistry induced in ices of different composition. And here again, you see the infrared spectrum of an ice before the exposure to the ion beam, and what happens, how the chemistry is affected by the chemical composition of the ice is affected by radiation. We use these experiments in particular to focus on the production of aldehydes, acetaldehyde and formaldehyde, that are considered precursor of more complex organic molecules. So what happens in the ice is that with irradiation, the precursor containing carbon, in this case methanol, is efficiently destroyed by the ion beams. In this case, we have experiments that were performed in Catania, but also with another setup, which is at the Institut d'Astrophysique Spatiale and at the Irène Joliot-Curie lab of the Université Paris-Saclay in France. What you observe here is the decay of methanol. So we produce fragments and radicals that become available to trigger chemistry, and we observe the formation of new species. In particular, we reported about the formation of formaldehyde and acetaldehyde. In the case of acetaldehyde, we see how its abundance increases with increasing the radiation dose, which we can relate to the time scale of exposure of an ice to energetic particles. We also see how its abundance depends on the composition of the ice, and on how, on the contrary, formaldehyde reaches a peak of formation at about 10 electron volts per molecule. But if we keep irradiating the ice, we are destroying these compounds up to basically its non-detection. Now, if we assume that formaldehyde is one of the precursors of complex organic molecules, this experiment shows us that if we expose an ice for too long in space, we will destroy the precursor of complex molecules. So an ice will be depleted of these molecules, and we cannot expect to detect relevant quantities of complex organic molecules in such a body. If together with ion irradiation, we simulate other processes that can happen in space, the chemical complexity of surfaces can be even more rich. In this case, we are seeing a water, methanol, ammonia ice, again exposed to irradiation, and we see how its chemical composition changes. And what then happens if we also simulate processes such as heating, which cause the diffusion of molecules in the ice and further reactions together with the sublimation of the most volatile compounds, is that we form a very complex and reddish material that we call organic refractory residue. You can see here image of this kind of material that was acquired with the instrument, with the microscope available at the Soleil synchrotron in France. Now, this material is since a long time well studied, well characterized, and it's considered a good analog of cometary complex organic, but also of the organics that can form, that are present at the surface of trans-Neptunian objects. So spectroscopy tells already quite some information about how complex can be its chemical composition. We see quite some infrared absorption features, so we have hints that this material can be pretty complex. But things are way more clear if we analyze this kind of samples with high-resolution mass spectrometry. These are some mass spectra that we acquired with the Orbitrap instrument at the lab of Véronique Buisson at the IPAG in France, in Grenoble. And what you see here are three different samples, three complex or three organic refractory residues, which were produced by giving to the ice different amount of radiation. In particular, we increased the dose from the top to the bottom. The chemical analysis that was performed revealed how the composition of these samples depend on the irradiation dose that we use to produce them, and thus on how the dose, which is connected to the timescale of exposure to cosmic rays of solar particles in space, can significantly alter the chemical properties of the organics at the surface of pristine bodies. What is also interesting to notice here is that each of the peaks that you see here is attributed to a stoichiometric formula. And looking at specific stoichiometric formulas, we also identified isomers of amino acids and of nucleobases. So these compounds, these organic refractory materials that we produce in the lab, can also be used to shed light on the astrobiological relevance of the complex organics at the surface of TNOs, that because of their location, I think we will never be able to explore, or maybe at least not in the next decade. So they become relevant sample for the understanding of how complex can be the matter in these objects so far in the solar, that are located so far in the outer solar system. So what do we see is that cosmic rays, solar particles can interact with simple ices, and that in both the scenarios, in the nature scenario or in the nurture scenario, the interaction of simple ices with these energetic particles can explain the production of complex molecules. The problem is that complex molecules are very liable to radiation because of their chemical nature. And once exposed on an atmosphere surface in a body which does not possess a magnetic field, cosmic rays and solar particles will significantly interact with this material till their destruction. This is a nice cartoon that also shows how cosmic rays determine changes in the properties of the minerals of exposed surfaces. So these alterations are even more significant in organics and in biosignature. So what we can do in the lab is also study how long would it take for organic matter and biosignatures to be altered in space by energetic charged particles. In particular, I will show you two examples. The first one is the study of organic revealed on the dwarf planet Ceres during the Dawn mission. Ceres is the first asteroid that we ever discovered in 1801 by Giuseppe Piazzi, which was a Sicilian astronomer with observation from the Observatory of Palermo. Asteroids are very complex to be observed because they are relatively small and dark. So the Dawn spacecraft was a unique tool to explore the composition of Sirius, the properties of Sirius. And the instruments on board the spacecraft acquired the spectra that you see in this plot. The blue spectrum is the average composition of Sirius, and then the yellow spectrum is the is representative of the composition of these yellow spots that we see here, very localized on the surface. And the presence of this absorption feature tells us that organic matter is present. Now, Sirius is a very interesting body because it's differentiated. We know that its surface is rich in minerals, clay, there is a lot of ice, and under the surface that might be quite a significant amount of other ices that surround a rocky core. So getting information on what happens on the surface might also reveal interesting information on what is going on below the surface that we observe. And this we will see is relevant for what concerns the origin of the organics that we detect. So what we did was to bring in the laboratory a material that could be a laboratory simulant, an analog of the surface of Sirius where we detected organic matter. And this was done in a collaboration with colleagues in Rome, in Florence, and in Naples. We produced these a set of samples made of minerals and of undecanoic acid, which was representative of the aliphatic organic detected on Sirius. And we exposed this sample to an ion beam. What we observe from the red to the violet spectrum is that this feature, a 3.4 microns that is observed in Sirius, is efficiently destroyed by radiation. If we analyze this spectra by a quantitative point of view, we are able to estimate cross-section. In particular, we performed the experiment using this Sirius analog, and we exposed it to different ion beams. You see, we kept the energy constant, but we changed the ion. We used proton, helium, and nitrogen ions. And that was meant to obtain a precise estimation of the cross-section value. So let's say an estimation of how efficient is this destruction process by solar particles on Sirius. Then we combine this number with a model that is able to inform on the flux of energetic particles at the surface of different bodies in the solar system. It's the OMIR software, which was developed by the French Space Agency in collaboration with TRED. And so using this, the combination of models and experimental data, we obtained information on the lifetime that organic matter can survive on the surface of Sirius. In particular, we simulated different cases, changing, let's say, the surface properties, changing the porosity of Sirius, and simulating the different lifetime of organics as a function of the depth in the asteroid. And that's because the particles can penetrate different depths in a body according to their energy. The higher is the energy of energetic particle, the deeper it can penetrate in the ice. So we here make two cases. If organic rich materials are found on the surface at the very, let's say, within the 5 microns from the within the surface, they can survive very short times, a million years, while if they're buried a bit deeper and within 100 microns, they can survive up to tens of years. But what these experiments are definitely saying is that what we are observing cannot be pristine matter that has been on the series of on the surface of Sirius since its formation. There must be some mechanism that determine the exposure of organic matter that is possibly buried below the surface, that for some mechanism was recently exposed on the asteroids. So enabling us its detection. I previously mentioned also biosignatures. You know that the solar system contains plenty of moons. Here's our moon, but the giant planets, Jupiter and Saturn contains hundreds of moons. And among them, we know there are moons that are rich in organic matter. Titan is maybe the most evident case where organic are present also in its atmosphere, and lakes of hydrocarbons are present at its surface. There are then other objects, such as the Galilean moons of Jupiter, that are expected to contain liquid water in their interiors. Now, the presence of liquid water is, of course, associated to life, because that's one of the mandatory things that life needs to here on our planet. And so there might be life under the icy crust surface of these objects. And whether there is life in their interior, some biosignatures might be able to escape, for example, in the plumes that were observed in some of these satellites. In particular, there is this nice paper by Potsberg and collaborators that use Cassini data to identify macromolecules in the ejecta of Enceladus. But to detect biosignature, we have to be sure that they survive the harsh radiation of space. So how could radiation change alter the or maybe hinder the detection of organics on the moon? Well, we take an example by analyzing the organics at the surface of our moon, where they were revealed in samples from the Apollo 17 mission. Here you see a grain of organic rich matter, or maybe better to say carbon rich matter, which is intimately mixed with gases in the moon regolith. What is the idea of Thomas Kepta and collaborators that reported about this detection? That organics arrive on board of meteoritic material. They landed on the moon, and then in not very constrained timescales, they suffered redeposition process, and they became trapped in the mineral matrix that surrounds them in the regolith. But so what could be the lifetime of an organic matter on the surface of our moon? For how long can it survive because of the exposure of the harsh radiation in space? Again, we performed experiments where we used a variety of organic molecules, and we exposed them to radiation. In this case, you see an experiment where we used one of the organic refractory residues produced in our laboratory that simulate meteoritic material. And we exposed it to energetic charged particles. As you can see from the black to the blue spectrum, we see a decrease of the infrared absorption feature of organics. As in the case of Sirius, we performed a virus experiment, also using different ion for the radiation, and we estimated the cross-section of the process. This data was then coupled with the flux of energetic particles that reach the moon. That was again estimated with OMIR software. And here is what we found out. So again, you see a plot that show you for how long organic matter could survive at the surface of the moon and as a function of the depth. In the case of radiation from galactic cosmic rays and from solar energetic particles. In particular, you see that we have various curves that are informing us that the lifetime depends not only on the porosity and on the barrier depth of the organics, as we've seen in the case of Sirius, but it also depends on the different irradiation source that you take into account. Galactic cosmic rays have a lower flux than solar energetic particles on the moon, so organics would survive for longer timescales if we only take into account this family of particles. But also the organic composition plays a relevant role. In fact, if we expose complex organic, they can survive for timescales that are even longer than the life of the solar system. While if we take into account organics of, let's say, with a more simple chemical composition, we, for example, investigated CH4 or formamide, their lifetime can be significantly reduced. But yeah, let's say that organic residues are the most representative of the materials that can be delivered on the surface of the moon. And so these experiments show that yes, organic can survive for timescales that are long enough to enable us their detection. And with this, I move to the conclusion. I hope I gave an overview of how relevant are these laboratory experiments to inform us on the chemical changes that can be triggered in interstellar ices during the star formation process, and also during the lifetime of icy surfaces in space. In particular, we have seen how organics are basically everywhere in the solar system, and we can use their presence and their distribution to shed light on how and when bodies originated, as it has been recently shown in the case of trans-Neptunian objects. We also have seen that energetic processing by cosmic rays and solar particles is extremely efficient in forming complex organic molecules and also refractory organics in space. And the information that is relatively new on how irradiation dose, so the extent of energy, the amount of energy that is absorbed by surfaces, can significantly determine the chemical composition of organics. And because the dose is related to the timescale of exposure, the chemical composition of a surface also depends on how long, since how much time this surface is exposed to energetic radiation. Finally, for what concerns the destruction of organics, we have seen how the exposure of atmosphereless surfaces to cosmic rays and solar particles can hinder us their detection, with the lifetime that depends basically on the flux of particles, on the barrier depth, but also on the composition of organics. And in this case, we observed how meteoritic complex organic matter that can be delivered by impacts is pretty resistant, as an example, on the surface of the moon. So with this, I would stop, and I thank you all for the attention, and I'm open to any question. Thank you.
Thanks a lot, Riccardo, for this very interesting overview about the reactions of organics with irradiation. And now we have actually open time for discussions, contributions, and questions. As you know, you can do it in two ways. Either you add the questions in the chat, or you just raise your hand, and then we will give you the word to speak. Please do not forget to unmute yourself then. Anyone coming forward? Serge, please. Sergey, please. I think you're still muted, Sergey.
Yeah. Can you hear me?
Yes, now
Yes.
we can hear you.
Okay, good. Thank you. Yeah, thank you, Riccardo, for this very nice presentation. It was very interesting. Yeah, I just have a short question regarding the initial conditions in the interstellar medium about the dust particles. So, because you demonstrated how efficient destruction of the organic could be, but at the same time you refer to CO and CO2 molecules as a precursor of the organic. But is it based on some kind of estimation, and could be a large portion of this actually molecules be a product of destruction of the organic molecules?
Thank you. It's an interesting question. In our perspective, what we want to simulate is, let's say, the stage 0. So you have the accretion of a CO, let's say pure CO on the backgrounds. No, it can be. This is, let's say, in the case of interstellar grains. There are various models that explain how interstellar grains are, icy mantles are made, and there is a model that suggests that you can have a layered, let's say, ice, and where one layer might be containing relevant amount of CO. So studying how CO is altered by radiation, it was meant to inform on the production of other molecules that then we detect in the star-forming regions. In that specific case, we use the radiation of CO to explain the detection of these carbon chain oxides in the gas phase of star-forming regions. So in our idea, CO-rich ice, which is contained in icy grain mantles, could be exposed to radiation, and in timescales of 10 to the 5, 10 to the 7 years, you could produce these carbon chain oxides that for some mechanisms could then be injected in the gas. The other mechanisms that you mentioned is the, if I understand correctly, the possibility of the other process. So you have complex organics which generate simple molecules, and that is something that we did not simulate in our experiments. That are some experiments which, for example, are performed on organic rich material covered by water ice to study the formation of these of CO or CO2 at the interface of the of a carbonaceous rich grain and ice. So yes, in principle, we can simulate all these aspects, but what is important for us is to have observational constraints that tell us, let's say, that what we simulate can be meaningful to the region that we want to simulate. So that specific experiment was meant to reproduce the abundance of C2O and C3O, for example.
Yeah, okay, thank you. Yeah, it's clear. I just mean that it would be, of course, also interesting just to try to estimate how efficiently CO and CO2 could be produced by the destruction of the organic, and yeah.
Definitely. Also because those are, when you take, for example, a very complex material and you expose it to radiation, those are two of the most abundant byproducts of radiation of complex organics. And there is some work going on that. I don't know the details though. So I think there's quite some nice stuff on that side.
Okay, okay, thank you very much.
Thank you.
Any more questions?